we have scheduled something like 30 minutes per talk, so please stick to the time. I'll remind you there, because I guess and I hope there will be time for discussion. And with having said that, I think we should jump directly to Andrea with the first contribution.
Hi, can you hear me?
Yes, excellent.
Okay, and now you should see my slides as well.
Yes, we do.
Confirmed.
Perfect. Thank you very much. Okay, so thank you for inviting me. I'm here to talk on behalf of many people that have been working on Patatrack, which is actually kind of a vague thing. So I'll start talking a bit about that. And I also mentioned here people that have been working tangentially with us, because they have been working on the HSF project, which has some overlap of what we are doing. So this is a non-exhaustive list of people. I hope I didn't miss anybody important, but in case, let me know and I will update the title slides later on. So to begin with, what is Patatrack? When I was asked to talk here, it was not very clear what the main interest would be. And initially, I didn't know this meeting was going to be joint between the Computer Accelerator and HSF. So I was going to talk a bit more on the computing and performance side and less on the physics, but I've added also some slides on the reconstruction algorithms and physics performance. Hopefully, some of my colleagues that are present can help if they have questions, because that's not really my main topic, but let's see how it goes. So first of all, what is Patatrack? The best I can say is that it's a loosely defined group of people working on R&D and the use of accelerators in CMS. Initially, we were based at CERN. Now we have people at CERN, but also colleagues at Fermilab and Casus and Aachen. And depending who joins the individual projects, other institutes or students passing by and so on. And as I mentioned, in the last couple of years, there has been quite some overlap with the HSF project to explore different performance portability solutions. It's also an incubator of ideas and R&D efforts. Over the past 4 or 5 years, we have worked on many different algorithms and their implementations. We are now working on performance portability solutions. To investigate this, we have developed a couple of standalone demonstrators, but the goal of what we're doing is that when we find solutions, we work to adopt them in CMS Reconstruction and in CMSSW. So all this exploration is interesting in itself, but the goal is always to have something that eventually we can use in the official experiment reconstruction. It's also a forum where we try to promote the use of GPUs and accelerators in CMS. We have organized multiple hackathons where everybody is welcome to join and try whatever they feel like, new algorithms, new hardware, and so on. We try to document our efforts, and we have organized some knowledge transfer seminars where we involve experts from specific detector or reconstruction algorithms and work with them to make it easier for them to start using accelerators and GPUs. And since the last year, we now have a closer collaboration with Casus because they have joined CMS, so we are collaborating, of course, on the use of Alpaca. And finally, what many people actually think about when they mention Patatrack is one of our main and first deliverables, which was the CMS pixel-only track and vertex reconstruction. This is something we developed for use at the HLT, targeting initially phase 1, and now this is under development also for the phase 2 detector and slowly being expanded to maybe some more complex environments like the heavy ions reconstruction. As I mentioned, we have organized multiple meetings and hackathons. Just, of course, this has been harder in the last couple of years for obvious reasons. But despite the restrictions, we managed to have a very successful hackathon last November, just with not very many people, because we could only have 2 or 3 people per group. And the main topics there were, again, Alpaca, but also the use of MPI, the optimization of the performance of our algorithm, and so on. So it was quite interesting to have this bunch of people work together in person after 1.5 years of basically only remote work. Now, let me start with the Patatrack pixel-only track reconstruction. The overall approach that we are following, what this reconstruction follows, is that it works on individual events. There is no event batching. There is no batching at the level of events. We do run the concurrent reconstruction on multiple events, but this is handled by the outside framework, not by the reconstruction algorithm itself. This because the CMSSW framework is fully multi-threaded, and this has been adopted also in the use of GPUs. So we can schedule algorithms running at the same time, and whenever the occupancy of the GPU allows it, different kernels will also run concurrently. The algorithm does a full reconstruction of pixel-only tracks and vertices on GPUs, starting from the unpacking of the raw data and going through the chain of modules and algorithms that you see here on the side. The reconstruction, or actually the running of these modules, reuses the on-demand features of CMSSW. So this means, for example, that we do the copies from the GPU to the CPU only if there is a CPU module consuming the structures. And we convert to the legacy data formats from the SOA optimized ones, again, only if there is a reason, because there is a module consuming them. Otherwise, the reconstruction can run entirely on the GPU itself. And the main reason is to minimize data transfers, because, of course, we don't want to move data back and forth between the CPU and the GPU. So the whole chain of algorithms is available on the GPU, even if individual ones may not gain particularly from the offload. The gain comes from having the whole chain running asynchronously and sequentially on the GPU. To give you more details in the full workflow, we start copying the raw data of each individual event to the GPU. This is order of 200 to 150 kilobytes per event in our case. For example, this is based on proton-proton collisions with around 50 pileup events. Then each of these boxes runs one or more kernels to decode the raw data, build clusters from pixel hits, build hit doublets, then use these doublets to build entuplets, which can be triplets, sorry for the type, or quadruplets, using a cellular automaton algorithm. Then we clean up duplicates using a fishbone algorithm. And once we have the full entuplets, we move on to the track fitting step, where 2 algorithms are available to fit the track parameters, either a Riemann fit or a broken line fit. We can apply some quality cuts on the results, of course, and then these tracks are used to build pixel-only vertices. As I mentioned earlier, only the final results are copied back to the host, and only if needed, they are converted to a legacy format. All of these algorithms have different parallelization strategies, and the main lesson here was that there is no one-size-fits-all solution. Really, for each individual algorithm, we had to investigate what kind of parallelization could be implemented in the algorithm and what parallelization levels would actually give some benefits in the performance. So starting from the first one, the unpacking of the raw data is parallelized across all the input pixel hits. So for each hit, we read the data from the ADCs and convert it into more human readable, or actually computer readable format. Then the clustering of the pixel hits is parallelized across the pixel detectors with, like, in CUDA parlance, 1 block per detector, and then across all the input pixel hits with 1 thread per hit. The conversion to global coordinates is parallelized across each cluster. We don't need to take into account the pixel detectors anymore here. Moving on to the next step of the reconstruction, we have the entuplets building. Here, the building of the doublets is parallelized on the hits of each layer. Now, the combination of doublets into entuplets is actually a two-dimensional parallelization, both on the inner and outer layers of each doublet. What I mean, on the inner hit and outer hit that come from the two different layers of each doublet. And then the cellular automaton algorithm runs a depth-first search, which is parallelized against all the combination of doublets. Finally, the cleaning of the entuplets uses the fishbone algorithm, which is designed to merge overlapping entuplets. And here again, this is parallelized in 2 dimensions over all possible entuplets, and for each entuplet with a small number of threads over the possible duplicates. The last steps are the track fitting. As I mentioned before, we have 2 alternative implementations of 2 algorithms. Both of them are implemented using the Eigen C++ matrix library and are parallelized over 10 entuplets. So we use 1 GPU thread per entuplet. And finally, for the vertex reconstruction, which starts from all the quadruplets above a customizable threshold, the tracks are clustered based on their position along the z-axis. The first parallelization here is done across all the input tracks, and then there is a quality applied to the vertices, so low quality vertices are split, and this is parallelized, of course, across the individual vertices. So as you can see, all these different algorithms are parallelized based usually on their input quantities. And this can be done in 1 or 2 dimensions or with different hierarchies, depending on the physics process itself. Now I have a quick look at the performance that was achieved implementing these algorithms. I'm not going to go through every single plot, but if you have any questions, we can look at them offline or afterwards. The main point, starting from the first plot, is that we have 3 quantities to compare. In black is the performance of the reconstruction, the pixel-only reconstruction that was used at the HLT in CMS at the end of round 2. And this was based on the reconstruction of pixel quadruplets, but the track fitting was done based on only 3 of these hits. Then in red, you have the performance of the Patatrack pixel quadruplet reconstruction. And you can see that this achieves over the whole eta and PT spectra better efficiency than the previous one. And in blue, you have the performance of the pixel of the Patatrack reconstruction when we require only 3 hits per entuplets or triplets. This, of course, achieves a much larger efficiency, but it also incurs in a much larger fake rate. So while the use of quadruplets can be done without applying additional requirements, the use of triplets can only be done in cases where additional information can be used. For example, triplets can be matched to the pixel vertices after they have been built, or they can be matched to other detector components like calorimeter deposits. So overall, the main advantages of the Patatrack reconstruction with respect to the legacy one are an improved efficiency overall, as I mentioned, a much improved or reduced rate of duplicate tracks, which means tracks where the same simulated tracks are reconstructed more than once, without incurring in an increase in fake rate as long as we use only, or actually an improved fake rate as long as we only use pixel quadruplets. The other benefit is that instead of using only 3 points, we now have a full 4 or 5 points track fit, which means we can achieve a better resolution of the track parameters. And this can be seen basically in all of these plots. Sorry. So if you have if you want to see more information about these algorithms or the performance, the three main resources I can suggest, apart from asking questions, of course, is the paper that was written about it a couple of years ago, the talk that Felice gave jointly, again, a bit more than 1 year ago at the CERNIP Software Seminar. And we have also have some more recent results in the phase 2 upgrade TDR for the DIQ and HLT, even if these algorithms are already being used for on-tree. Now, moving on to the latest topics that we are working on in Patatrack, this is mostly performance portability. So just a disclaimer, while the results I showed before have been approved and can be found already published, all the results that I show next are very preliminary, meaning that we have been running jobs overnight and this morning to give you the latest and greatest version of the performance of the code. The downside is that we have run this on a single or a couple of machines, so this has not been validated across all possible architectures, all different software versions, and so on. So my request is that please do not reshare these results or use them for any assumptions, but if you're interested in getting some recent results, get in touch with us and we can validate whatever can be used outside of this talk. So the R&D on performance portability started quite some time ago, honestly. And this has been based on a simplified version of the CMSW framework and the Patatrack reconstruction. The first work was done almost 3 years ago, based only on the first of these boxes. So only on the unpacking of the raw data into digits and clusters. And this is something that Matti set up quite some time ago, and we used to investigate at the very early stages of our studies how to port this reconstruction from CUDA to CPU implementation, but also how to use Alpaca or Coccos or SQL and YPI. Then, starting from a couple of years ago, Matti again set up a much more comprehensive project, which is linked here. You can find it on GitHub, which has been used both by the Patatrack and the HEPCC's attempt to evaluate different performance portability solutions. It's based on a simplified version of the CMSW framework, but it still has full support for building and loading plugins, for multi-threading based on Intel TBB, and on asynchronous work. The advantage it has minimal external dependencies. So apart from the library and framework that one is studying, like CUDA or HIP, the only dependencies are TBB, Booster, and I think we have the dependencies of these projects like HWLock library to print nice backtrace. This is everything, I mean, all things that can be downloaded and built locally without much hassle. Then what was done was to extract the CMS reconstruction algorithm from the CMSW implementation itself into this self-contained project. And this includes the pixel lock and reconstruction and the Patatrack pixel-only track and vertex reconstruction. It also includes a minimal validation of the results of the reconstruction, so we know when things are working properly or not. And of course, being much simpler than the full CMSW framework, this is extremely useful for prototyping different solutions, like different ways to interface the framework with the Accelerator API, and to port to different hardware and software architectures. So, and also run benchmarks on these different machines. So to give you an example of running on different hardware, this is an easy one. Here is a comparison of the performance that we can achieve running this full pixel track standalone reconstruction on 3 NVIDIA GPUs in the same server machine. This is a dual Xeon Silver with 20 physical cores. And running hyperthreading, we have 20 threads, 20 hardware threads available. On these machines, we are comparing the performance of an NVIDIA Tesla V100 from the Volt architecture with 5,000 threads, of a Tesla T4, which is a much smaller GPU, especially in terms of power consumption, only 70 watts instead of 300 of the V100. It has half as many threads as the V100 and half as many memory. And finally, a more recent NVIDIA A10 GPU, which is from the latest Ampere architecture, which, depending how one looks at it, has either 9,000 or 4,600 threads, 24 gigabytes of RAM, and it's an intermediate working point in terms of power consumption at 150 watts. And here you can see the performance of these different GPUs of running a single reconstruction job as a function of the number of concurrent CPU threads and concurrent events, but also effectively CUDA streams used in the job. And you can see that while with the T4, we basically saturate immediately or pretty quickly the performance of the GPU. For the V100 and for the A10, we do saturate things with 6 to 8 concurrent jobs, but then we saw a drop in performance. And we can see a bit later on why this is the case. So we can already use this to compare the peak performance of these GPUs with respect to the nominal parameters and, for example, published peak flops per second. In the case of the comparison of the T4 to the V100, we see that basically things scale with the number of threads. And the other improvements in the V100 with respect to the T4, like the increased number of double precision floating point registers, is not of particular use to our software. For comparing the T4 to the A10, we see that the performance is more than twice that, which, if you consider the full 9,000 threads, is a bit disappointing. But then once you start looking at the details of the architecture, you see that actually these 9,200 threads are actually 4,600 floating point threads and 4,600 threads that can do either integer or floating point operations. While the T4 and V100 have, for example, 2,500 threads for FP32 and 2,500 threads for in32. So what NVIDIA quotes here are the FP32 threads, but they're actually shared with in32. So if you take all this into account, the clock speed, etc., we see that the A10 should achieve twice as much the performance of the T4. It gets a bit better. This is like 2.1 to 2.3, if I remember correctly, which means that we're actually able to use some of these share in32 FP32 threads to gain some extra advantage. An example of different software solutions we can use. This is something that was developed originally inside CMSW, but it's much easier to look at this standalone context. So as I think everybody here knows by now, memory allocations are extremely expensive in a GPU context. And this is true both for the device memory, like what you get from CUDA-malloc, and from pinned host memory, what you get from CUDA-malloc host or similar APIs. The main reason is not the allocation itself, but the fact that these allocations incur in a global synchronizations across your whole job and everything that's using the GPU. So if we run our software using only CUDA-malloc and CUDA-malloc host, meaning allocating and freeing memory buffers for each event, we get a horrible performance. We get order of 250 events per second on the A10 GPU. NVIDIA improved things significantly with the introduction of stream order memory operations available from CUDA 11.2, I think. because they avoid global synchronizations across the whole GPU. This is implemented internally using a memory pool, which leads quite naturally to stream-ordered operations. And if we use this, we see that the performance increase is quite noticeable. We go to order of 1,300 events per second. However, already before these were introduced, we have been doing better, if you want, because in CMSSW, we have been using a caching memory allocator, originally based on the one in the CAB library, both for the device memory and for the pinned host memory. The advantage is that it can be used also for host memory, but also that it does not require special support in the driver of the runtime. So this was already available in older versions of CUDA, and it's easy to port to other architectures like ROCm. And using this approach, we get peak performance that you have seen before. We reach around 2,300 events per second. And then investigating how this allocator is being used, we saw that this drop in performance as the number of threads increases is actually due to the contention in the allocator itself. And this we had figured out because by replacing the mutex used here with something which is faster, even with a higher CPU occupancy like a spin lock, the performance flattens without dropping with the increase of threads. This is still not what we use by default, because this measurement and the measurement in a full CMSSW application are quite different things. So of course we want to validate in the production environment before deploying things, but this is already a quite useful approach to study how different solutions behave in a simplified scenario. Finally, coming to performance portability, with a standalone application, it's obviously much easier to try to prototype, sorry, this was out of place before, to try different backends than with a whole CMSSW application because of the much smaller dependencies. And so this application has been ported to AMD HIP and ROCm. We have started porting it to the Intel One API and SQL-based implementation. And also we're testing different solutions like Cocos and Alpaca. So on these two plots, we compare the performance of the native implementations with what we got from Cocos and Alpaca running on the same GPU. So you have in blue the same performance as before from running with native CUDA on the A10. In yellow, the performance when using Alpaca on the same GPU on the same machine. And in red, the performance when you're using Cocos in the same configuration. And here you can see that using Alpaca, we are now able to achieve basically 95% of the native performance. And the same holds true when we run on the CPU only. We have a version of our code that has been ported to run on CPU based on some ad hoc solutions implemented within the CMS. And then we have the performance that you get from using Alpaca. And in this case, we see that actually with Alpaca, we get a better performance than the native one. We don't know exactly why. We're happy that it's better and it's not worse, what can I say? We try to investigate where this could come from, but so far without much luck. So the bottom line here is that in part thanks to these investigations, and in part, of course, by other R&D aspects and in-depth comparison of the performance and features of Cocos, Alpaca, and One API, and also joined with the effort under the HAPCC project, CMS has decided to adopt Alpaca as the solution for performance portability in Run 3. The main use case is to run the high-level trigger software, which originally has been developed for CUDA, which includes at the moment the Patatrack reconstructions, but also the calorimeters for reconstruction on different GPUs, for example, AMD GPUs, automatically ported to run on CPUs, replacing the in-house effort that we have done. And of course, once the migration from the native code base to one based on Alpaca is complete, we can benefit from any other platform that Alpaca gains support for. For example, at the moment, SQL-based platforms like Intel One API, but also Xilinx FPGAs are in an experimental stage in the head of the Alpaca developments. So to conclude, the Patatrack effort has been kind of the catalyst for the adoption of GPUs in the CMS reconstruction. As a result, CMS is now deploying a GPU-equipped HLT farm from the very beginning of Run 3. The machines are now at 0.5 and are being bored in and commissioned. And based on the amount of code that we have running on CPU and GPU, the balance that we have found is to have machines equipped with a dual Milan AMD EPYC processor and dual NVIDIA T4 GPUs. All the CUDA-based algorithms are fully integrated in CMSSW, and new ones are being developed. And we have the choice of performance portability library has finally fallen on Alpaca, at least for Run 3. Now it's likely too late to deploy this at the HLT this year. So what we're targeting is actually the Monte Carlo production campaigns later in the year, and of course, deployment online in the HLT starting from next year. It's a very interesting time to work on these topics. The R&D landscape is wider than ever. We are working on integration of portable modules and data structure in CMSSW to try and make the kind of diagram that you have seen in one of the first slides as automated as possible. We're, of course, developing new algorithms and porting existing ones to GPUs. For example, particle flow algorithms are now being ported to GPUs, but also algorithms specifically for the phase 2 reconstruction. One of the next issues we have to tackle is to find an efficient way to share a local GPU between CMSSW and machine learning frameworks, for example, O1NX. And of course, we are working in close collaboration with the Casus group on Alpaca. So we are pushing the functionalities provided by Alpaca to try and cover as many as possible of the CMS use cases. For example, we are now trying to find a way to support CUDA and ROCm in the same binary, not just in the same source code, but also be able to build a single binary that can run on both. And this is something that we have done with a trivial example, but not with Alpaca, so that's the next step. And as I mentioned, we have developed some optimizations like memory caching allocator in CMS, and it's probably interesting to try and refactor it into a standalone library that anybody could use on top of Alpaca. There is also now some ongoing work on the use of remote GPUs over efficient network, as I mentioned in PI before. So there are plenty of topics that people are working on and we are investigating. So if you have any questions, you can address them now or later. I don't know what's the preferred approach.
Thank you, Andrea. Excellent. I see there went 3 virtual hands up already. So I think we can jump into the questions. Let's start with Charles.
Thank you, Andrea. That was really, really interesting. Do you envision any other uses of the, or users of the GPU in the HLT other than Patatrack? And do you think that a T4 will really be sufficient if that happens? And what is your, do you have an upgrade plan for that? Because I can't really imagine finding T4s for the next 5 years is going to be particularly easy.
So currently at HLT, we are running the Patatrack reconstruction, so the pixel-based one, and the colorimeters local reconstruction, which actually is an even larger share of the HLT CPU usage right now. The plans are to try and extend it to include also, maybe not this year, but certainly the next years, some of the particle flow and electron reconstruction. So we do have interesting other use cases apart from Patatrack at HLT. Now about the use of the T4s, I don't have these results here, but I can share them later. They will be in a proceeding, but I presented them at ICAT last year. What we saw is that a single T4 would not have been enough to run the full HLT on these huge CPUs. Keep in mind that these CPUs have 64 physical cores each, so we are talking about 256 threads overall. However, with 2 T4s, we think that we have capacity to spare. This is because if you take into account how many nodes we have running, the full GPU reconstruction goes faster than how many events the HLT has to process. So we know that we have spare capacity. If this is enough to cover all the use cases, I can't say. It will depend how intensive the new use cases will be. This is something we have to see case by case. And then coming to the second part of the question about possible upgrades. At the moment, we don't have upgrade plans for these kind of machines because we chose machines which are compact enough despite the leafy CPUs, so they can only fit T4 GPUs because they are low profile ones. We could probably change a bit the style of machines to move to something like an A4000, I think, but something like an A10 doesn't fit. So the plan is if we need to upgrade the CPU and GPU balance, either we buy more machines and we leave part of the CPU unused on the old ones, or we push on the effort of using GPUs on remote machines, which is something we're considering, but only as a very, very, very early R&D project.
Thank you, Andrea. Attila, you're next on the list.
Yeah, I'm sort of riddled with questions, but let me just ask one, I think, relatively simple one. So if you go back to page 14, I found this, this performance plot pretty interesting. So I can well imagine, and your explanations seems perfectly plausible that it's the caching allocator that produces that dip on the more performant GPUs. But why is there no dip at all on the T4? That seems to behave a whole lot better.
So my interpretation of the results is that so keep in mind that this is a kind of unrealistic workflow, at least for our production case, because the large majority of the algorithms are running on the GPU. There is very little happening on the CPU. So if you profile these jobs with the standard caching allocator as we have now, you will see that like 90% of the CPU is waiting for the GPU to finish, or waiting for the lock on the caching allocator. So if we remove the lock of the, if we replace the lock on the caching allocator to use STD mutex and instead use a TBB spin lock, then the second part becomes much faster and all the waiting is just waiting on the GPU.
No, I think I understand that.
And then in the T4, the GPU is lower, and so the second part matters less.
Yeah, exactly. Since the GPU is slow enough, the CPU threads don't step on each other because they are just all waiting.
Exactly. That at least is my interpretation. I cannot prove it.
Okay, thanks.
Thanks, Andrea. Then I think you also posted the question in the live notes. Very
yes.
Go ahead, please.
I did post them in the live notes. Actually, I have many questions. Thanks, Andrea, already for a very interesting talk.
Let's try to go to 1, 2, that we have enough time. And pick your most.
Yes, no, I think the most relevant one is just to know about thread divergence. I mean, do you have any assessment of whether your algorithms are in lockstep or not? And and how many tracks or pixels do you have to do you typically have? Because okay, let's say typically you have is it 32 threads per warp? I think that you need to fill in to have let's say a good use if you have lockstep. And related to that, have you tried vectorization on CPU, since this is a bit related? Okay, it's a bit different, but it's very related.
Okay, so I don't have a general indication of how much the threads are in lockstep or diverging. We have looked at it with the profilers many times, but it's kind of hard to get the conclusive results because every time we try changing something based on what the profiler suggests, things actually become worse. And also these algorithms are all very different from each other. So, for example, in the case of the track fitting, the algorithm is pretty deterministic in the sense there are very little branches, so we expect things to be pretty much in lockstep. In the case of the clustering algorithms, since they are iterative, we expect things to run different number of iterations, so some threads will finish earlier and they'll have to wait. But that's kind of part of the algorithm itself. About the use of vectorizations is not something we have looked at. It is something that we intend to look at. One reason is that clearly if an algorithm can run in lockstep on 32 threads in a warp, it should be reasonably easy to vectorize it. And the other is more specific to how we build these things. So in CMSSW, we try to build the whole code base in the same way, and then enabling vectorization for all of it, we don't see any gains because there is a lot of parts which don't vectorize well. And it also means we cannot run on older architecture. Now, I'm not the right person to say why, but we are still supporting architectures as old as CC4, I think, so without even AVX. However, when we build, so one improvement in the recent years is that we can now build individual libraries for different versions of CPUs. So we could build some specific libraries for AVX2, AVX512 in order to try to get some benefits of vectorizations. And if you put these two things together, that we have this nicely wrapped algorithms coming from the GPU and the possibility of building individual libraries with vectorization, it's quite obvious that at some point we're going to try put the two things together and see if we gain anything.
Thanks.
Thank you. And then I think we'll get to Marco as the last question and follow-ups. Please, Andrea, I'll just put you out there. I hope people would just get to you if they have particular questions which we cannot address now.
Absolutely, I will also try to answer directly on the live notes.
But Marco was still waiting, so it would not be nice to cut him off here. So here we go.
Hopefully a quick one. If you were to start a new project and you need to accelerate it on a GPU, would you use Alpaca directly, or you will analyze it in CUDA first? So, like, is for you Alpaca completely equivalent to just using plain CUDA?
Right now, I would say that Alpaca is 90% equivalent. There are a few things that are missing and that we're working together with the Casus group to implement. And then there are a few things which are a bit more cumbersome. For example, using a profiler is it's not more complicated, but it's less immediate because you get kernel names which all look like each other, so it's more difficult to see at a glance what you're looking at. I mean, you can dig into it, but you just need a very large monitor to see the details. On the other hand, if I would be starting a new project with the goal to eventually port it to different architectures, I would definitely start with Alpaca from the beginning, or something else if it fits better. The point is, most of the work is writing the algorithms. So starting with CUDA anyway is a very good start. But if you plan to move to something else later, you might as well start directly that way.
Thank you very much.
Thanks, Andrea. Again, for this extremely interesting talk, sparked a lot of discussion and to be continued, I'm pretty sure. Let's go to Bianchi then for the second contribution. We have roughly the same time, so Bianchi, if you stay in time, we also have time for this discussion afterwards. And I'll give the floor to you.
Okay, can you hear me?
Yes, yes.
Okay, and you see the slides.
They're not in full, they're not, yeah, now they're in full window view. Go ahead.
Okay, thanks. Okay, thanks everybody for joining the forum. So this talk is about the HTS prioritization R&D effort, and my name is Bunky, and I'm presenting here on behalf of the HTS project. So as everybody might know, there are like a good motivation for GPU track reconstruction. So the first thing is that the track reconstruction of the HRLHC will face into the huge computation, and so the conservative logic model for the CPU computing is quite pessimistic, and the major software development is necessary for the acceleration of the online and offline computing. And many people think, including the HTS community, the GPU might play a key role with the higher speed and the lower power consumption beyond the conventional the CPUs. And the most important thing is that the track construction problem is inherently parallelizable. So it's a good fit to the GPU offloading. So in HTS project side, it's been a while. Actually, we have started studied the GPU offloading for some cases. So basically, the HTS is like the general track reconstruction toolkit for the general high energy physics experiment. It's an open source, and it has a very good thread safe design, and it adopted the modern C++17 concept. And as I said, yeah, we have studied some core algorithms for track reconstruction, which has been ported for the CUDA and Seeker. As you can see on the right plot, one is for the CUDA seeding, and the other is for the GPU command filtering with the simple geometry. But it's also obvious that there will be the clear limit when it comes to the full offloading the track reconstruction algorithms, because not all the C++17 features is not supported inside the device code, and some event data model and GPU geometry should get GPU friendly to be used inside the GPU. So that's the one thing that we need to solve for the full GPU offloading. So the HTS community has decided to work on the GPU demonstrator by launching the several R&D projects. And so this is the very simple schematic of the R&D project for the HTS parallelization. So we have launched 4 projects. The first one is the TrackCC, which is the downstream project, and it is the demonstrator for the tracking algorithms in the GPU. And that ray, yeah, because we need like a GPU friendly geometry, so that ray is dedicated for the GPU geometry building. And we have the Algebra plugin, which is used by the TrackCC and that ray, and it provides the vector and the matrix algebra for the like a different multiple plugins, including the iGen, and the Vecman, which is the upstream project, is the GPU memory management tool. So the Algebra plugins, Detector, and TrackCC, all of them are using the Vecman library for the GPU memory management. And so let me briefly introduce the what is the Vecman and how what is the each conceptual design for GPU memory management. So the bottom line of the Vecman is makes use of the STD-PMR memory resource to customize the allocation scheme in the host side. So it can support the CUDA Seeker HIP as well as the CPU. And the convenient thing of the Vecman is that it provides the STL-like containers for the host side. So we have like the Vecman vector, which is the alias of the standard vector, and we have the jagged vector, which is the typically the vector of the vector. When you also have the Vecman array for compile time memory allocation, and this is for the host side. Because we cannot use the STD vector inside the device code. So we have like the counterpart containers for the device side. And so for the Vecman vector, we have a Vecman device vector. And for the jagged vector, we have the jagged device vector, etc. And this kind of the STL-like containers are extensively used for the Detector and TrackCC to describe detector and event data model. So yeah, we can just like customize the memory resource or the allocation scheme by just making the memory resource dedicated for each API, as you can see in the right code. And so the how to use it is very easy compared to the raw the GPU API interface. So we just create the Vecman vector, and with the memory resource dedicated for the target API, and we just pass them to the data object, and the data object are passed to the CUDA kernel or Seeker kernel, whatever the target API is, and we just like create the device vector inside the kernel device. So yeah, that's how we use the Vecman all over the Detector and TrackCC. And let me move on to the Algebra plugin, which is going to be quite short. So as I said, it's this is the plugin which provides the vector and matrix algebra. So this Algebra plugin includes the multiple plugins. So one is the homebrew array plugin, which is built on top of the standard array, and we also have iGen 3 and S-matrix from the root and the VC library. And currently, we are focusing on the development of the matrix operation per thread, which is quite the conventional way to use the algebra inside the GPU. But we are also planning to add operations per block to benefit from the GPU architecture with the massive parallelization. So so we will get back to this in the later in the TrackCC side. And let me move on to the Detector project, which is the GPU geometry builder. And so the motivation of the project, as I said in the introduction, the current HTS geometry highly relies on the runtime polymorphism. So, and this is not very GPU friendly because it's very like tricky to use the bare pointer or the virtual classes inside the GPU device. So the goals of the project are building the tracking geometry with the Vecman based containers, and we want to be capable of translating the HTS geometry into the data geometry, so we can just make use of the predefined geometry from the HTS side. So the final output will be the classes for the GPU-friendly detector and its sub-detector components, and also the realistic magnetic fields for the realistic propagation of the tracks. And we also want to provide tools for the geometry navigation with the proper stepping algorithms. And so this is the conceptual design of the D-tray detector. So yeah, as I said, the D-tray detector is fully based on the Beom-based container, and all the detector subcomponents are serialized inside them, and the subcomponents are interlinked with an.
We lost the sound.
Yes.
Yeah, me too.
Okay. Bianchi, we lost your sound. He probably don't know if he hears that.
Beom, can't hear you.
Maybe stop his share so he notices.
I pinged him on Skype as well to see if that's.
Sorry, what happened?
Here we go. Perfect. You're back.
So did I lose?
We just lost your audio for a bit.
Okay. For how long?
For about a minute.
About a minute. Okay.
Yeah.
I think it's okay now because I.
Yeah, it's okay. So just go on, please. Yeah.
Yeah. So okay. So let me just go from the beginning of this slide. So so the general concept of the data rate detector is as I said, the detector subcomponents are serialized in the Beom-based container because we have defined the detector with the Beom library, and all the subcomponents are interlinked with an index rather than a pointer to avoid the runtime polymorphism, but to use the compile time. And for the detector description, we have like several kinds of the subcomponents. So the highest level component is the volume, which keeps the indices to the surfaces and portals. And the surface and portal, they are the surfaces which keep the indices to the mask and transform. And the portal is just the kind of the surface which connects the two neighbor volumes. So it's defined at the edge of each volume. And the transform, which is linked to each surface, they contain the metrics for the local to global transformation. And the mask is just the shape of the surface and the dimension of or size of the surface. And we finally have the surface grid, which is the two-dimension grid of the surfaces. And they provide a neighborhood lookup for volume local navigation. So if you see the right side, you can see how all the subcomponents are interlinked to each other. And this figure is for the XY tomography of the surface grid, define the data ray. And so how we offload the detector geometry to the device is pretty similar with what I explained for the Beom interface. So we define the host detector with the Beom vector by just putting the vector type into the detector template, and we just elevate them to the data object with the data vector view classes, and this detector is passed the CUDA device corner or any other API corner, and we can create a device detector with the Beom device vector. So the in principle, the host and device trait of the detector is fully depends on the Beom device, Beom container type. So for example, for Beom vector, it is defined as the host, and for the device vector, we can define the detector for the device side. And so another interesting study for the realistic magnetic field is has been done with the NVIDIA GPUs with the texture memory. And so what has been studied is like the how we look up the magnetic field and how we can do the interpolation with the built-in hardware inside the NVIDIA GPUs. So because it's just like a built-in hardware, there is no any software overhead. So it's like a the fast interpolation method for the magnetic field. And actually the preliminary result for the CUDA kernel time for the rendering is quite short, like a 20 millisecond for the like about like more than 1 million image, 1 million pixels. And as you can see on the right side, you can see a very beautiful picture of the Atlas magnetic field rendered at when the jet is equal to the 0. So this is one of the promising study that we are doing for now. And for the propagation, so this is for the propagating the tracks inside the detector, inside the DTRA detector. And we have like 3 core classes for the propagation. And the first one is a stepper. And the stepper, they change the track state based on the stepping algorithm, such as the linear stepping or adaptive Runge-Kutta-Nystrom first order method. And we have another the core class which is called navigator. And this navigator is for like the guiding the track propagation into the right way, so they don't miss the surfaces during the propagation. So because they need the geometry information, they take the detector as an input argument. And as you can see in the right diagram, they find the candidate surfaces in a volume by shooting like a linear ray, and they just like expect which surfaces the track is gonna reach inside the volume. And when the track is, while the track is propagated, they also update the linear distances between the track and candidates and decide the track is on the surface or not based on the linear distances between them. And also they give like the step size limit to the stepper so that the stepper don't do the like overstep over the surfaces. And the propagate is just like the combination of the stepper and navigator, which steers the workflow of the stepper and navigator. And so this is the propagation speed benchmark for the DTRA. So we have tested it for the pixel detector part of the trigonometric detector, and we use the Runge-Kutta stepper with the 2 Tesla B field. And we have tested with the 2 different plugins for the homebrew array and the iGen plugin, and also for the single and double precision. And the left plot is showing the result for the single precision, and right one is showing the double precision result. And as you can see, the first preliminary benchmark result is quite promising. We got like 1 order of the magnitude of the speed up. It's about like 10 to the 4 tracks. And yeah, so yeah, it's quite promising that we got the like a 1 order speed up with the CUDA API. So because this has not been optimized very much a lot yet, so we can expect more speed up in the future. And so so that was about the DTRA. Now let me move on to the TrackCC, which is the downstream project for the final GPU demonstrator for the tracking algorithms. And so the right the workflow is showing the the general the track reconstruction algorithms. So in track CC, we aim for the demonstrating the most of the tracking algorithms on the GPU, including the heat clusterization and the seeding and the Kalman filtering. And as I mentioned in the introduction of the talk, the event data model are fully based on the Beom-based container, and we are currently focusing on the CPU and CUDA and Seeker API, but the HIP and the std-par API will be investigated over time. And so this is the sub algorithms for the heat clusterization part, which is the first stage of the tracking. And the core part is the cluster making algorithms, which is called the connected component labeling and also called CCL. So here we just make the cluster of the heats inside the detector modules, and from the the clusters, we calculate the weighted average of the cluster cell positions and the covariances. And so once we make the measurement from this calculation, we convert them into the space point by doing the local to global transformation. And those space points created will be the inputs to the seeding algorithm. And so this is the current progress in the heat clusterization. So because there have been like the technical difficulties in the defining the clusters, EDMs, with the Beom library. So we somehow wanted to skip this explicit cluster EDM, and by just combining the CCL algorithms with the measurement creation. So this is somehow like similar to the connected component analysis, which is called CCA. And we have like investigated the fast SB algorithms for the CCA, and the preliminary result showed the very promising result with the CUDA API for the like more than 10 to the 4K modules. And the second stage of the track reconstruction is the seeding, and they also have like a couple of the sub algorithms. And the first one is the space point binning, where we group the heats on the two-dimensional grid. So the reason for the grouping the heats is like so for the specific bin, they just like look up the neighbor bins, so they don't have to waste time by looking at the random space points inside the full detectors, because there is not many possibility that the space points will make the seed in the far regions. So that's why we do the space point binning. And we also have the seed. After we do the space point binning, we move on to the seed finding, which is also like divided into the doublet search and triplet searching. And once we find the triplets, we do some filtering for the triplets. And once we find the seeds, we estimate the track parameters by doing the global to local transformation on the surface. And the bound states on the surface will be the input to the Kalman filtering. Actually, this seeding is the most extensively studied part of the track CC so far. And inside the inside the GPU API, each sub algorithms of the seeding parallelizes over the space points, doublets and triplets. So they are like fully distributed on the GPU architecture. And we have studied the seeding with the CUDA and Seeker API. And as you can see on the right plot, we see about one of the over the magnitude speed up with the CUDA and Seeker compared to the CPU, which is the GCC and compiled by GCC and Clang. And we got the similar speed up for the single precision and double precision. Of course, double precision the speed up in this study is quite lower than the single precision because we just use the RTX 2070, which doesn't have any dedicated hardware for the double precision. But this study is quite promising so far. And what is interesting is that the secret showed like the 10% better speed up compared to the CUDA. So this is the prospect for the future command filtering in the TrackCC. So this may not be the final decision that we might have for the command filtering because it's a very important part of the TrackCC and we might need more discussion in the future. But there are generally two schemes which is under the discussion. So one way is doing the command filtering for one track, which is assigned for per thread, and the other scheme is one track per one GPU block. And actually, both schemes have the pros and cons. So the advantage of the one track per thread approach is it's pretty easy to implement algebra. For example, we can just use the Eigen library right away for this study. But the disadvantage of this approach is that we might get suffer from the branching conditions or branching divergence, as you can see in the right diagram, because when let's say we have the tracks distributed over the blocks, and each track is assigned for each thread, and let's say the first track came across surface, and they have to run the command filtering, which means that any other a thread which has to be synchronized to the first track should get either out of it. So that's the one the big the big disadvantage we have for this approach. So the second approach is solve this difficulty by just assigning the one track per block, because the thread inside in different blocks doesn't have to be synchronized at all. So this approach is free from the branching divergence issue. But one difficulty is that it's going to be very hard to optimize the algebras in a given dimension of the threads. So yeah, that's some ideas that we have for the future command filtering, and we'll see how it goes in the future, because we don't know which one is going to be better in the end. So we need to to study as much as possible. And also in HTS design, the command filtering is just an extension of the propagator, which is the part of the D-tray. So it closes the loop to the D-tray project once it is done. So this is the summary. So HTS R&D projects are being developed to offload the tracking algorithms onto the GPUs. And the Vecman, which is the upstream project, is the core library for defining the detector geometry and event data model based on its the STD-like containers. And the algebra plugins provides the essential algebras to data in TrackCC, while the efficient matrix algebra is under development and discussion. And the D-tray constructs the direct tracking geometry for the command filtering with the propagation. And in principle, the detectors are fully usable in host and device side without any modification. And the benchmark study on the propagation is promising, but still a lot of works remain to be done for more flexible detector design, and also for the HTS geometry translation. And TrackCC is the downstream project for GPU tracking demonstration, and it has successfully demonstrated seeding algorithms on CUDA and Seeker. We plan to harmonize with the D-tray detector for implementing command filtering. So as a final remark, if you want to join or participate the R&D effort for the parallelization in HTS, you can join the bi-weekly HTS parallelization meeting at the Friday at 16 p.m. in Sun time, and you can also contact us with the mailing list written down here. So that's all. Thanks a lot.
Thank you, Bianchi. Very good. There is one question from Vincenzo. Vincenzo?
Yes, can you hear me?
Yes, very well. Go ahead, please.
Okay, thanks for the all these details about ICTS on the which I didn't knew was so advanced. So in many slides, you present a speed up of the GPU versus the CPU of, say, factor 10, if I well understood. On the other hand, given the fact that the growth is linear with the complexity of the problem, I think that the full GPU is used. But now you compare with a single CPU. And from my understanding is that in general, the cost of a GPU as the one you use is equivalent to a CPU with 32 or 48 threads. So could you comment on this? I have also another question related to this about SQL. What's the backend of SQL here? Maybe you can answer to this question first because it may be trigger another question.
The backend for the SQL, I'm not sure if I understand correctly, is the SQL 1 API with the Clang from the LLVM.
It's the front end.
No,
What's the back end device?
As you can imagine, it is running on the same NVIDIA card as the CUDA version. So so SQL is building an NVIDIA binary. The Intel compiler is building an NVIDIA binary in this case, and we are comparing how fast it runs against the native CUDA version of the code.
Okay, so this is the SQL which does either jitting or ahead of time compilation for CUDA using the Clang compiler for CUDA.
Yeah, yeah. I believe in this case we don't ahead of time compile. It really is jitted.
Yeah, okay, but
yeah.
It
doesn't matter much.
Produce the same code for CUDA. And you have not tried to use Clang native without SQL.
No, I didn't listen in this study.
So you don't know if this is due to NVCC versus Clang or because of the SQL, nobody knows what runtime. Okay, can you then answer? Sorry. Okay, this is great. Thank you for this clarification. So, and what about instead the
let me answer.
With respect to the C++ code? Because you have not tried SQL on C++, right? You have not tried SQL on CPU.
No, I didn't use the SQL for the CPU.
Yeah, that would be nice, interesting. Because if you have the code for SQL, maybe you can just, just change device. It's one line, and try SQL on CPU.
Yes, we did. We did try that. It performs horribly.
You did try that? I didn't know that.
Yeah. The very latest version of the code does work on a CPU, but this just very nicely underlines why even in the long run, I don't think that we will ever be in a situation where we will just have a single algorithm, a single source file that will run efficiently on a CPU and on a GPU, because the version of the SQL code, which runs pretty much on par or even slightly better than the CUDA code, then we run it on all of the threads of our 16-thread CPU, it performs worse than a single thread of the CPU specific code. So yeah, it technically runs and it produces.
It could be, but
result,
maybe you can try to run a single CPU. So now the point is, as you said, that the CPU has 16 threads. So, but the single CPU is going only 10 times lower than on the GPU. So if you run 16 jobs, you will go faster.
Yeah, I mean, let me comment it. Yeah, that's right. It's right that if we run the multiple CPU, whatever the GCC or Clang is for the CPU, yeah, the gap between the CPU and CUDA, or the CPU and between the CPU and SQL will be like a very small. But the thing is that if I can make an excuse for that, we didn't even try to use the multi-threading for the CUDA or SQL, because for CUDA we can try to use the CUDA MPS, and the thing is that the one event for the seeding doesn't really occupy the entire resources of the GPU device. So there are like some rooms to get the extra speed up with the multi-threading with the GPU APIs still. So yeah, the study is not quite completed yet in terms of the multi-threading, as you commented out. So yeah, this is somehow will be the direction for the future study.
So just to underline this a little bit, your point is very correct. The results that we show here, these are just something that we could do now. These are not results that we would base like hardware purchase on. But the situation is actually a little bit better than what these results even show, because when we look at these extremely simple test jobs in a profiler, let's say when we look at the NVIDIA profiler, it tells us that yeah, running the entire seeding, including copying data to the GPU, copying stuff back, that would take I don't even remember what the amount of time was, but so we measured that entire time. But when we just look at the profiler, okay, how long did the kernel actually take? It's a fraction of that time, because there is just a lot of overhead with copying stuff around, the CPU preparing the next kernel. So we are hopeful that once we do the proper measurements, we will be able to still get speed up even when we are running with a lot more threads than this. But we have to do this. So we didn't do that work yet.
Very good. Just to add, I add one sentence before I'll ask Liz to have a question. The idea of this code is also that, yes, it should also be able to run on all CPU cores if you want to. Yeah, I mean that should be possible in the design of the propagation, for instance. So if that's the best option, it's the best option, and the code is there. Okay, Liz, can I ask you to?
Yeah, I guess I have a question about your, it sounded like you're kind of in the beginning of figuring out a strategy for the common filter part of this. Is that true? Did I get that right? Prospects?
I mean, this slide?
Yeah. Mm-hmm. Yeah, the reason I bring that up is because I'm wondering if you looked at the MKFit code and see what the weaknesses and strengths of that is when you're thinking about the design of this one.
Yeah, but MKFit is usually for the factorization
Yes.
of the track.
Well, that was my thought, was that vectorization and GPU are kind of orthogonal, but maybe the best of both worlds could be gotten by looking at both of these codes. That was my thought.
Yeah, I mean, I'm keeping an eye on it.
That's good.
Yeah,
Okay.
but as you said, that this point is a little bit, as you said, it's a little bit orthogonal to the what is the philosophy of the MK fit. Yeah, MK fit is usually for the data vectorization, and at this part of the prospect for common filtering, yeah, we might need the vectorization to utilize the massive parallelization, especially for the second strategy. Yeah, so I think it's worth to looking at it in more detail. Yeah, anyway, thanks for the comment.
But don't I remember correctly that MKFit uses a linearized parameter transport model?
And that, I know that it has a special standalone algebra library. I think it is for that. Yeah.
Because I mean, one of the, sorry, go ahead.
No, go ahead.
I mean, one of the primary kind of complications and major sources of complexity here is that the ultimate goal here is to run full-fledged numerical integration for the particle transport to run the Kalman filter.
That relates to another question comment I had. You earlier in your talk, like slide 3 and 9 or something, talked about data structures that would be friendly to GPUs. And I was really impressed by the magnetic field map too, by the way, because I saw it flash by. And I'm wondering, there is a CCE project kind of nascent, that is trying to look at data structures that would be friendly to GPUs. And I was wondering if maybe some discussion between the two groups might be useful. We don't have so I'm kind of a mentor in the CCE project.
I'm attending the CCE meeting every Friday.
Okay, all right. Well, so you're going to the Friday one, but the one that they're talking about, the data structures, is on the Tuesday.
Okay.
Yeah, so it does seem to, and I go to both. So it seems like maybe there's some disconnect here. I don't know for sure. Maybe Paolo I saw was also on this call, but yeah,
it's gonna be wonderful if we can share some experiences, and if we can get some like the ideas from them. It's gonna be wonderful. Yeah.
Well, I think actually you're a little bit ahead of them, but I think if just sometimes adding more manpower that can talk to each other, two people going in the same direction can help. So.
Okay. Yeah. Thanks a lot. Yeah, I will ask about the general meeting information to you or Charles.
Yeah. No, you can.
Yeah.
What a nice say final note for the meeting from the Hype Software Foundation that should bring collaboration together. I think that's exactly what these meetings are about. Yes, they're about to show the progress and the status and the ideas, but they are also to connect the community, and I think that's a real good example. So I'm very happy to have heard this discussion. Is there a final urgent question that people think or comment that is worth it to let everyone else spill over the 1800 cutoff, which we did by 3 minutes? Then speak up now. Since that is not the case, I think everyone, particularly the speakers, I think that was a real nice meeting. The attendance showed that this was also, I think, highly regarded by the community and waited for. So I'm sure we'll have some sort of follow-ups from this and other projects. And if it fits, doing it in a joint fashion in order also to bring basically the different aspects together. That is always a good thing. Graham, you want to add something?
Andrea, I think you summed it up beautifully, so I think we can close here.
Excellent. Okay. Well, then we see you in one of the next HSF meetings and other forums.
Thanks, everyone.
It's
Bye.
good. Bye-bye.
Bye-bye.